Okay, so are there any questions before we go forward? One thing that I wanted to mention is, so apparently anybody who sort of completed got pretty good marks on the LIST project, and some of you probably didn't complete and ran out of time. I did tell at least one person that if they haven't submitted it and they're still in the class, they can submit it by over the spring break, work over the spring break, and submit it, and then we'll use it for some partial credit. Okay. Since I said it to one person, I'm saying it to other people too. So anybody who either did not submit or got felt that they could have done better, if it's like 10%, it's not worth your time probably. I mean, although of course learning is always worth your time, but if you think you could have done double your mark and you have no spring break plans, then you can do this. Okay. Since I said this to one person, just to be fair, I'm saying it to everybody. The other thing I would say is that you have gone. I mean, again, it's a free country. You can decide when you want to drop a course. Since you're all here, you haven't yet dropped the course. I would suggest that anybody who had come up to this point probably wants to complete the course. Okay, so if you're worried about your grade, come and talk to me. Okay, in general, people who are worried already probably disappeared, and I think you've done a lot already in terms of the course outcomes. So I would suggest that if you're worried, come and talk to me, send me an email or something. After you drop, I can't do anything. Okay, so I mean you can still do whatever you want. I'm just suggesting this as a sort of a morale boosting if it would help. Okay, as far as the what's coming down the pipe is concerned, as I said, we have project 3, which is base networks, which is very similar to this project 2 in the sense it's mostly a modeling project. And then we will have the homework due basically by the end of the spring break. Okay, I think I'll add one more question to it. And then the next exam would also be very close to after the end of the spring break. I have to still set a date, but I think if you have already bought Fort Lauderdale or whatever spring break tickets, by all means keep them. But I think generally, if we're going to have one more midterm and then final, and the other midterm has to be sometime before March is over. Otherwise, the final and midterm would be at the same time. And as far as that next exam is concerned, it will only have propositional logic, satisfiability, and base networks. Okay, so anything else I do continue to do that won't be part of the midterm. And so you will have time to do the homework, and then after that you do the test. Okay. Yes.
And the planning graph, will that be?
Yeah. Thanks for reminding me. So in case there's a really nice planning graph question, remember his name. He's the one who suggested. Okay, yeah, that's true. Planning graph. Yeah, why not? Okay, so that's the situation. Any questions? Okay. So before I go forward with what I'm going to do today, I wanted to do something else, which is what's going on? Oh, there. Okay. The reason I'm going to that is that put it right there. Okay. First of all, are there any questions on what we've been discussing all this while? Everything is crystal clear, completely clear. Okay. So I guess what I'm going to do right now is sort of a waste of time because, but you you may want to. I just felt that the deseparation condition may have come across as a sort of a magic. Okay, I want to tell you that in fact it's not magic. In fact, it just comes from the definitions. Okay, and so remember for the deseparation condition we had 3 cases. This is evidence A, B. Actually, no, let me just look at this way. So I have A, B, C, okay, and B can be evidence or not be evidence. I have A, B, C. Okay, that's a different kind of a path. So this is causal chain. This is common cause. B is causing both A and C. So in fact, the right way to write this is A is causing B is causing C here. This here B is causing both A and C. Okay, and the third type that we considered was both A and C are causing B. Right? Okay, and then we were interested in the fact that in these 2 cases, if B is given, A is independent of C. If B is given here, A is independent of C. Okay, whereas in this case, if B is not given, A is independent of C. But B is given, it won't be independent of C. Right? I just said this, and I sort of made reasonable sounding arguments. Okay, but I think it's very useful to know that you can do this from first principles. And what I'm going to do right now is to show this case to you from first principles, and you will do these 2 for the homework. That's the extra question you're going to have. Okay, mostly this is just so that you can't learn magic. I mean, if you think something is magic, you won't remember it. So you should be able to know that if required, you can derive it. Okay, that's the basic idea. So I'm just looking at this particular case. Okay. Okay. So I have 2 situations. Situation 1 where B is not given. Right? B is not given. So there is no evidence in this case. Yes, sir.
Could you turn off the projective glares?
I can do that, but I think it'll be harder to look at it. Let's see. Can you people see this better? Okay, fine. So B is not given. Okay. In that case, if B is not given, again, what we are interested in seeing is you want to be able to show that A is independent of C. Right? Now, if there is no evidence, essentially you want to be able to say that PAC is PA times PC. That's the definition of absolute independence. Right? Okay? Now, from base network configuration, you know that PABC is PA times PC times PB given AC. Agreed? You should be able to see this, right? That's the whole point of base network thing, right? Okay, now from this, I want to derive PAB. How do I derive PAB from this? I sum over, I want to derive PAC. Okay, and show that PAC is nothing but PA times PC. Right? And this, so basically then I have to sum over the values of B. B equal to true, B equal to false. Okay? PA times PC times B given AC. Right? Now, this is actually part of what I'm doing here is also helpful in understanding the variable elimination. This summation is over B. The only place where B is occurring is here. Right? So you might as well move B, Right? What do you think that would be? What is that sum? 1, right? Because so B true given AC, B false given AC must add up to 1. Right? So this is 1, which means is equal to PA times PC. I just proved from first principles essentially that if you have a path like this in this small network, if I don't give anything, A is independent of C. Okay? I mean, you have a notion of what independence means, but really the definition of independence is this. If it holds, it's independent. If not, it's not independent. That's it. Any questions on this? Fine? Okay. Now, what I'm going to do now is the other case. So other case where A, C, and B is given. When you give it, you normally scratch it. That means that's evidence. Okay? Now, when it is given, then essentially the kind of independence you are talking about is PAC given B. If you really believe A and C are independent, must be equal to PA given B times PC given B. Right? So the question is that true? Always. Not just, notice that whatever I did here, irrespective of what the actual CPTs are, this will always hold. Right? It's not just once in a while thing. Whatever the CPTs, it will always hold. Okay, so the question is, well, can I do that here? So to do this, I need to compute PAC given B. And part of what I'm doing here is to get you even more comfortable with Bayes networks. I'm just doing joints, using the network configuration. So PAC given B is what? PABC by PB. That's a definition of conditional probability. Right? Okay? So now what is PABC? It's the same. PA times PC times PB given AC divided by PB. Unfortunately, this is not in general equal to PA given B times PC given B, which is not. For specific numbers, it may well be equal. Do you see what I'm saying? In fact, how can I make this be equal? Here is a scenario where I will give you a special case. So first of all, do people realize that this expression is not generally equal to this expression? Okay, but two expressions which are not generally equal can be made to be equal for specific values. Okay, so here is my idea. What I could do is, see, notice that, notice, suppose I have a situation, where, what should I want to do? Suppose A and C, let's see, how can we get this, for specific values. Okay, let's see. Take this. That one. Those three. Okay, it's an interesting form. Look at it's PA times B given AC by PB, right? Okay. By the way, if you understood this part, you already understood what I wanted to say. What I'm doing is a little extra. Okay, this is slightly more advanced. So suppose this was equal to P given A. If the numbers were such that PB given AC were the same as PB given A, then what would happen? This will be PA times PB given A by PB. What is that? PA given B. Okay? PA given B times PC. Okay? So then if it also turns out that PC, so in this case you realize that it's already, this part is the same as that part. Okay? And with additional structure on the numbers, PC given B will be just PC. And so for that specific case, it may well so happen that they are independent. Okay, so the explaining away doesn't always have to work, because remember, this whole example is about explaining away. Okay, and explaining away, for example, works in most common scenarios because you assume that it's unlikely for two things to occur simultaneously to cause C. But it's up to me to set up the numbers. And if I set up the numbers different ways, then in fact explaining away on that particular case might not happen. And so they will still be independent. But what we really care about is, irrespective of what the CPT is, it should be independent. That's not true here. Okay? By the way, this thing that I did here, okay, PB given AC, I made it into PB given A. In the other two cases, which you will do for homework, you would actually be able to get that without doing any assumptions. It will actually look like PA times PB given A by PB. And so you will wind up writing it as PA given B using base rule. That's how you will be able to see conditional independence holds. Because in the other two cases, when the evidence is present, the independence should hold. And when the evidence is not present, the independence should not hold. And the way independence held here when the evidence is not present is because B got summed out. In the other two cases, you know, basically, even if you sum out, it won't become 1. There would be more complex dependencies. Okay? Whereas on this side, when the evidence is there, you are looking for conditional independence, and it will hold. Because by Bayes' rule, you will be able to show that PAC given B is actually equal to PA given B times PC given B. Okay. It's both because this is kind of useful both because this way you know that directional independence is just a shorthand notation for something that you already know. It's not a made-up rule that somebody gave you as received wisdom. You see what I'm saying? It's just because you always start from this and this are the definitions of independence. This is the definition of absolute independence. This is the definition of conditional independence. And finally, since we are at this also explains why, if you're given a node, a given node is independent of everybody else when given the Markov blanket. Okay? Because what happens is, in that case, you can show to yourself that the last, so there is a blanket around the node. Remember, there is a, let's see, remove this. So this is the node A, and it has parents P1, P2, children C1, C2, this C2 has another parent, P3, this C1 has another parent, P4. And the Markov blanket would be these guys, these guys, these guys. And if that is given, if all of those guys are given, then A is independent of everybody else in the rest of the network. In this case, there is no more network. But suppose there's a huge network sprawling on all the sites. Okay, then what happens is you should be able to convince yourself that a path going from any arbitrary node to A will be touching the evidence nodes either this way or this way. In both cases, evidence blocks the propagation. Okay, so from definitions of conditional independence comes D-Sep, and from D-Sep comes Markov blanket. Okay, we will actually use Markov blanket today. So any questions? Like I said, there will be an extra homework problem added where you just show that other two cases also hold by D-Sep by just doing normal algebra given conditional probabilities. Okay, so in fact we will get here eventually, and this is a very powerful way to do inference over Bayes networks called Markov chain Monte Carlo, and it uses Markov blanket. So you will hear about it again today. But before that, I want to go back. Where we are. There. So last two classes, at least last class at least, we did exact inference on Bayes networks. We figured out how to do exact inference on Bayes networks. Okay, but Bayes networks are essentially, obviously the probabilistic networks. That they're about, the dependencies are all probabilistic. So one idea is, for example, sample the network. And if I give you enough samples, then you can do frequencies to compute any random probability. Okay? And that's what we will be considering in today. So how would you generate sampling methods? How would you come up with sampling methods to compute the probabilities? Any given probability, you should be able to compute the probability in terms of samples. Now, unlike exact methods, these methods are approximate. They will only be exact probability when, in the limit, when the number of samples tends to infinity. Okay? Anytime you're trying to compute a probability from estimates, from samples, you can always be a little wrong. Right? For example, I want to figure out what's the percentage of women in Tempe. This would be a really bad sample, right? So I would start with this sample and I would say, well, how many are 1, 2, 3? That's it, right? 3. So 3 out of whoever is the number is the percentage. That's the probability of finding a woman. If you take a random sample. Now, is that a correct number? No. But if you take more and more people in Tempe, if you as the sample becomes as large as Tempe itself, you'll get the exact probability. Okay, and furthermore, if your sample is more and more close to the demographics of Tempe, even with a small sample, you will get better probability estimates. This, unfortunately, is not representative of demographics of Tempe. It only is representative of demographics of computer science, for whatever reason. Okay? So what you really want to do is, in sampling-based methods, first question is, how do you get the right sample? How do you get a good sample of the underlying distribution? And secondly, you should be aware of the fact that even if you take all this, the numbers that you're getting depend on, the accuracy of the numbers depends on how many samples you took. The worst possibility is that the sampling method is innately biased. That even if you took all the samples, you will still get the wrong number. Suppose I try to estimate the probability of finding a woman in the random sample, of Tempeans. But my great idea is to call, randomly, pick a Tempe number and call. And whoever picks up, ask or figure out from their voice, are they male or female? Okay, and if you call, let's say, a million phone calls, and police haven't yet caught up with you, then you'll get numbers. But is that a fair sample? And another equal thing is you put a Facebook message saying, if you are from Tempe and tell me your gender. And some people will say male, some people will say female. Okay? And as you get more and more samples, would you get the right probability? Because a bunch of smart people don't actually have Facebook accounts. That's how they have a life, right? Okay, and so by avoiding the Facebook accounts, so you then essentially you're not getting Tempe population, you're getting Tempe population with Facebook accounts. So this sample will be biased. So how many ever Facebook Tempe people get back to you, you will still be getting the wrong number. Okay, long back in India, some magazine came up with this great idea that they can do election polling by just calling phone numbers. And there are only like 3% of the people used to have telephones, and only 2% of them are stupid enough to pick it up when there's a call, at the night time. And so based on that, they came up with who's going to win. Obviously, it didn't work out. And in US, the great example for that is Dewey wins. How many of you know Dewey wins? There was a presidential election where everybody was so damn sure of their exit polling that they actually published papers with headlines saying Dewey wins. And Truman actually won. And so there is the one famous photograph of Truman standing with Dewey wins paper. Okay? And of course, what happened? The sample was not representative. So how much ever you take, sample is not representative of your data. Okay, so in looking at the sampling methods, you will be interested in making sure that the samples are representative. That to do that, you need to be actually able to show that they are consistent. That means there is no bias. That means as the number of samples tends to infinity, the probability would be completely correct. All the methods I'll give you do have that property. I won't prove that here. The textbook actually has that information in case you're interested. Okay, but you do have to care about it when you are generating sampling methods. Okay, so the other interesting thing about sampling that I want to have in the background while we go through it today is, many a time I have to, when I'm doing sampling, I have to essentially toss a coin. Okay, probabilistically toss a coin. Now the question, of course, is how to toss a coin which is 0.5 heads, 0.5 tails. You have a coin for that. Okay, how do you toss a coin such that, suppose, I basically have to figure out that a particular probability, a particular event has a probability of 0.1. Now I need to figure out whether in my current sample is that event true or false. To do that, essentially, I need to actually toss a coin. Except the coin I'm tossing as heads 0.1, tails 0.9. And I still have to toss that coin. And if it comes heads, then E is true. If it comes tails, E is false. Since it's painful to generate these kinds of biased coins, what we do is we essentially have a little method. You have, in all computers, have random number generators. Okay, if you say random 0, 1, it'll give you a number between 0 and 1, a real number between 0 and 1. Okay, and rand 0, 1 is known to be, so it would be uniformly distributed. That means every real number in that interval is equally likely. And when you say rand, it will give you one of those numbers. Okay, then all I need to do is, so here is 0, here is 1. And if I'm trying to do this particular toss, then anytime the number I got is between 0 and 0.1, I assume it is heads. If it is between 0.1 and 1, I assume it is tails. That's it. Do you get this? So this is how you simulate coin tosses. because the rest of our discussion today will be tossing coins of various probabilities. And you don't have to go into what's called numismatics, which is basically, I mean, this is my old GRE vocabulary. I got to use it today. That it's coin collection, especially biased coin collection. You don't need to do it. Instead, you can just do this sort of simulated toss. Okay, fine. Okay, and in fact, you can also do three-phased coins with this. It doesn't make any difference. So, for example, if you have three possibilities, that possibility 1 is 0.1 probability, possibility 2 is 0.3 probability, possibility 3 is 0.6 probability, then I would say, I would again pick a random number, I just ask random to generate a random number. If it is in this interval, I would say it's possibility 1. If it is between 0.1 to 0.4, I'll say it will be possibility 2. If it is between 0.4 to 1.0, I'll say it's possibility 3. Okay? Fine? Okay, so now what I'm going to do is I'm going to tell you how to sample from the networks. And the simplest case, of course, is I don't have any evidence. I have a network here. Okay, I don't have any evidence at all whatsoever. So then basically I can ask general questions about joint probabilities. I can ask prior probability of cloudy. So this is a situation where I have cloudy, sprinkler, rain, wet grass, and this is the base network right there. This is the one I'm going to use. Okay. So I don't have any evidence, so this is my entire network. And so the kind of questions I can ask are things like, what's the probability of wet grass? Okay. Of course, what's the probability of cloudy is very easy to answer because it's right there. But what's the probability of wet grass? So what's the probability that sprinkler is off and wet grass is true? Those are all the kinds of questions that I can answer on the empty network because there's no evidence. Okay. So how do I do this? First, I generate samples. Okay. And then let's say I have an hour. I'll spend my time, and let's say not an hour, maybe a minute. Okay. I'll spend 59 seconds, 59.7 seconds generating samples. And in the last minute, I just use the samples to compute the probabilities. Okay? The generation of samples would be, basically the interpretation of the entire world. That would be a sample. So here's what I would do. I'll start from the top. Now I need to sample cloudy. How do I sample cloudy? I take a coin of 0.5 heads, toss it. If it comes heads, cloudy is true. If it comes tails, cloudy is false. You actually have to toss it. In the sense you have to simulate tossing, otherwise it won't work. Okay? Now, suppose in this case I tossed it and it came heads. So then I have cloudy is true. Now that in my sample, in my evolving sample, I already know cloudy is true. Now, because cloudy is true, sprinkler only depends on cloudy, right? So sprinkler essentially is going to be true with 0.1 probability and false with 0.9 probability. Do you see that? So now I get my 0.1 probability heads coin, toss it. If it comes heads, I'll take sprinkler to be true. If it comes tails, sprinkler to be false. Obviously, it's 9 times as likely to come tails than heads. But I still have to do it. Right? Okay, so I did my toss, let's say. So basically, I'm using 0.10. Because cloudy became true, the right number to use is 0.10. So I sample sprinkler now, okay, with 0.10 as the heads probability and 0.90 as the tails probability. And I actually tossed it, and it turned out that I was unlucky. So I got tails. So in this case, sprinkler actually came out as false. Okay. Now, I can also do the same thing for rain. Again, rain too depends only on cloudy. So I'm looking at them in the topological order. That's the idea. If you do it in the topological order, there will be some leaf nodes, because it's directed acyclic graph. There will be some root nodes. Root nodes can be sampled up front. The moment you sample root nodes, somebody's parents have been sampled now, and so they can be sampled, and so on. Okay, in this case, I get to sample rain. Rain, when cloudy is true, rain comes with 0.8 probability and doesn't come with 0.2 probability. So I again sample that. Okay, when I sample that, I get rain, in this case, true. Now at this point, I can sample wet grass. Okay, because both its parents are present. And its parents are sprinkler is false, rain is true. Sprinkler false, rain true. So this is the line I need to look at. Right? And now, in that case, wet grass is true with 0.9 probability and false with 0.1 probability. Okay? Right? So now again, I sample wet grass by tossing the coin with 0.9 heads and 0.1 tail. And then, in this case, apparently I did get wet grass true. So now I have generated an entire sample. My current sample is cloudy, no sprinkler, rain, wet grass. You know, obviously I went through it slowly, but your computer can do this in under microseconds. Okay? Then ask it to do one more, ask it to do one more, ask it to do one more, until you get a whole bunch of these. If you get a whole bunch of these, you essentially have an approximate idea of the joint distribution. Do you understand what I'm saying? So notice that there are only 1, 2, 3, 4. So there are only 16 different states that you can get. So as you keep sampling, some states keep coming more and more times. So if you sampled 1,000 times, and this thing came 5 times, so the probability of this entry is 5 over 1,000. So this way I will know the probability of all the joint distribution entries. Right? Okay? At this point, once I know the probabilities, estimated probabilities of the joint distribution entries, I can compute any probability I want. Right? Yes?
But if we are given this network, then we can directly compute the joint probability, right? Why we
This is what I'm doing. So the interesting, that's a very good question, by the way. Okay. So the idea is this network is small enough that the joint distribution will only have 16 entries. What if I have a network whose joint distribution is 3 billion entries? And furthermore, to generate those 3 billion entries, I have to do 3 billion multiplications, maybe of the order of 3 billion multiplications. Here I'm not. I'm just directly generating samples. Okay? So you have to convince yourself that by doing this, you're doing less work, essentially. And at some point of time, the work you do this way would override the work you would have done by actually generating the entire joint. At some point of time, going through Facebook or telephone or looking at the student union to figure out what probability and what percentage of people in Tempe are women is going to take more time than asking all the Tempeans to come to a town meeting and just counting them right there and then. Okay, yes?
So what's a good way of determining the sample size?
That's a very good question. For sampling problems, essentially, normally, if you come up with a sampling algorithm, you're supposed to come up with bounds, and they're much harder to come by. So I won't tell you any right now. Okay? I will tell you, however, methods which tend to converge faster than other methods. I'll at least tell you 2 methods today. One is way better than the other method. So it has better sample efficiency. Okay? But coming up with actual bounds is much harder. And normally, even when people come up with bounds, they'll be very loose. Okay, but that's a very, very good question. That's what, if you say, I have a better sampling algorithm, and you want to write a paper about it, what you need to do is show the bounds, essentially. Okay, or at least compare it to other sampling algorithms on some benchmarks and say you're getting by faster with fewer samples. Any questions on this? Yes?
There might be the case that there is more than one root node, right?
Doesn't matter.
So you will iterate both together at that?
No, basically, no, I mean, all I'm saying is just look at nodes, sample nodes in the topological order. If there are 2 root nodes, then all the root nodes would have been sampled before any non-root nodes will be sampled. That's all you care. Okay? This is the basic idea of our sampling. What I'm going to do now is, generally, you would not actually be asked to, I mean, this way you are essentially computing the entire joint by sample estimation, and then using that to figure out various probabilities. Okay? However, many a time what I will know is I might actually basically tell you an evidence. I would say, I already know that sprinkler is on. I already just observed that it's pouring outside. So I'm giving you evidence. Okay? So then the question is, how do I sample from the evidence? Now, of course, you could do, even if there is evidence, you can do it this way and compute the conditional probabilities, right? Because PA given B is PAB by PB. And you can get PAB from this, PB from this. But if you have evidence, it's better to sample directly such that you are consistent with the evidence. Do you see what I'm saying? So that's the next method. That's what we're going to look at next. Okay? That is basically the simplest idea is rejection sampling. What happened to my rejection sampling? Let's see. Wait, no. So the rejection sampling, I'll show it to you with respect to this. I seem to have lost my picture. And so, even though it says likelihood weighting, right now, first I'm going to use this same slide to describe rejection sampling. Then I will describe the better idea called likelihood weighting. So in the case of rejection sampling, I will do just like before. Okay? So in this case, what I know is sprinkler is true, wet grass is true. Okay? So I want to compute my probabilities given sprinkler true, wet grass true. Okay? So what I can do is, I will once again generate, so I want directly the entries that describe this conditional probability. The sample should all be consistent with the condition, with the evidence, right? So I would start from the top. I would do cloudy 0.50, and then let's say if cloudy comes true, then I will sample sprinkler. If in my sample sprinkler comes true, I'm happy. If it comes false, I reject the sample. I just reject the sample and start all over again. Because the sample I'm just about to generate basically is inconsistent with the evidence. Why generate the sample? That's called rejection sampling. Okay? So essentially, all you do is, in the case of rejection sampling, so to generate the estimate P rain given sprinkler equal to true, for example, you use 100 samples. Suppose you generated 100 samples, of which only 27 actually have sprinkler equal to true. That means you threw away 73 samples because they were useless. And of those 27 samples, you check how many had rain true, how many had rain false. 8 had rain true, 19 have rain false. So the distribution of rain is normalization of 8, 19. So 8 by 8 plus 19 and 19 by 8 plus 19. Those are the probabilities. This is rejection sampling. Okay? Now the problem with rejection sampling is that it is sample inefficient. It generates samples and throws them out. In this particular case, it generated 100 samples and threw away 73 of them because they were inconsistent with the evidence. Now, here is a very interesting question. Suppose I have a situation, okay, I have a network, which is a long, pretty deep network, and my evidence is at the bottom. I sample all the way down, and the likelihood that I'll actually agree, but any of my samples will agree with my evidence is lower. So I would construct the entire sample only to find that it's not agreeing with the evidence and throw it away. The deeper the evidence nodes are, the less likely that you would actually keep the sample, because the sample is not likely to be consistent. If the evidence nodes are higher up, it's simpler. Right? So basically, in this case, you have done all the work that is needed to construct the sample, except you don't get any benefit. Right? Okay? And this kind of a thing happens, particularly in real life too. For example, I might be interested in finding what is the probability of having runny nose given Ebola virus. What is the probability that a random sample will have Ebola virus true? Very, very low. So most of the work you do, you would waste it. In fact, runny nose is 100% probable when you have Ebola, because everything is runny when you have Ebola. Right? However, about 1 billion people, if about 1 billion samples, the number of samples that will have Ebola is maybe 3. And it turns out all 3 also will have runny nose. So the conditional probability is 3, and conditional probability is 1. But the prior probability of Ebola is very low. And if you have evidence, so you know that in this guy's case, I know that the guy has Ebola. So what's the probability that they have runny nose? That, essentially, you would waste a lot of time making samples, throwing it away, making samples, throwing it away. Do you see what I'm saying? For example, if you're interested in finding out what is the probability of finding a random Tempian who is male and college educated, and you are standing in some flea market and taking random people. Most people probably may be from Tempe but not college educated. Okay? Or you can be in ASU, in which case most people may be college educated but not from Tempe. I don't know how many of you are actually in Tempe. They may be from Mesa, they may be from various other places. Okay? So you are constructing samples and you're losing, basically you're picking a sample and it cannot be used ultimately. Okay? That's the problem with rejection sampling. So this is the case where it will do a lot of work to get to the same level of accuracy. That's your point. Okay? So then I will tell you an idea, which is a beautiful idea. This idea, the fact that this idea works should not be surprising to you. Because you're getting samples and you're only taking the samples that agree with the evidence and of which you're considering the portion where rain is true. And you shouldn't be surprised. You probably won't need a huge theorem for you to believe that as the number of samples increases from 100 to million to 10 billion, this probability distribution will be more and more accurate. So if you were to compute it using exact inference, it would be the same as this. Okay? But here you're losing the effectiveness of the sample you generated, because you're generating a whole bunch of useless samples. Right? So what I would like to do is, rather than say, the problem with our samples is either it is a sample or it is not a sample. It's binary. That means either it's agreeing with the evidence or not agreeing with the evidence. Right? What if I say it's a 0.1 sample or 0.03 sample? That means I need to push it to agree with the evidence. And the amount of push I have to give it to agree with the evidence is going to define its weight. If it has to be really pushed hard, it's not a very good sample. If it just by itself becomes consistent with the evidence, it's as good as 1. Do you see what I'm saying? That's what I want to do. That's basically the idea of likelihood weighting. Okay? And doing it is not that hard at all. Essentially, instead of just having samples which are all of weight 1, now you have samples of weight 1, weight 0.7, weight 0.001, and so on. And you count the number of samples in which the rain is true divided by the weighted summation. So you basically take the weighted ratios now. Do you see what I'm saying? That's what I'm going to do. And to do that, I have to essentially generate samples and give the weight for the sample. Previously, all the samples had weight 1. Because if you generated a sample at all, it had weight 1. All the 0 samples, you threw it away. Okay? So what do we do here? In this case, I start from cloudy. Okay? Right? And right now, I keep this dynamic parameter called weight, which is the eventual weight of the sample I'm going to construct. In the beginning, the weight is 1. So whatever sample I'm constructing will, amount to 1. Basically, one good sample. But as I do crazy things, its weight becomes less and less compared to 1. It'll never increase more than 1, but it'll become less than that. Okay, so now anytime I play by the rules and actually sample, I don't change the weight. Okay, so in this case, I sample cloudy, and cloudy became true. Okay, so now I have cloudy true, which is part of my sample, and its weight is still 1.0. Now I have to sample sprinkler and rain. Okay, now rain I will sample. And so because of rain, the weight won't change. Sprinkler I really don't want to sample. I want it to be true because evidence says true. So my question is, what do I need to give you so that you will let me keep sprinkler to be true? Well, if cloudy is true, sprinkler being true is only 0.1 probable. So you have to multiply your weight by 0.1 so that I'll let you do this. That's the penalty you pay because you didn't actually toss the coin. Okay? So I now, basically I keep sprinkler as it is. So because of which I take a penalty of 0.1. Then I sample rain, it came true. When I sampled rain, it came true. I didn't do anything illegal, so my penalty doesn't increase. It remains the same. At this point, I must keep wet grass to be again true, because otherwise I wasted my effort. Right? Okay. Now, what would my penalty be to keep wet grass true? Sprinkler is true, rain is true, true, wet grass is 0.99. So I must multiply that by 0.99. At that point, I get the effective weight of this sample. It's not a 0 sample. In fact, the other guy would have just rejected this sample because they would have said it's just 0 weight. It's not 1 either because you're taking, licenses, essentially. You see what I'm saying? Right? Now, the interesting question, so its actual weight is 0.099 in this case. So I have one sample, cloudy, sprinkler, rain, wet grass, true. So CSRW, and which is 0.099. And I might do one more sample, it might say CSRW 0.01. One more sample, not C, not S, R, not W, 0.4, so on. So now I have a whole bunch of samples, their weights. And if I want to find out what's the probability of rain given this evidence, I take the weighted samples, the cumulative weight of the samples in which rain is true, divided by the cumulative weight of all the samples. Because all samples satisfy evidence. Do you get this? Cumulative weight of samples where rain is true, divided by cumulative weight of all samples. This is obviously not as easy to see right away that it would work. So in fact, you need to prove that it actually converges in the limit to the true probabilities. There is no bias. I won't prove it here. You can look at the textbook. There's a short proof there. But that's one of the nice ideas. Okay? So likelihood weighting is much more sample efficient, than rejection sampling. And one of the things I'm actually considering doing is that, in fact, it should be easy for you guys. It may be harder for you to write a code for variable elimination algorithm, maybe. But it should be very easy to write a code for given a particular Bayes network, sample from the network. And in fact, it should be easy to convince yourself empirically that this guy, the rejection sampling idea, is way better in getting the same level of accuracy. It can get to this particular level of accuracy with much fewer samples and so much less time than rejection sampling. It's a very good idea. And one question that you might be wondering about in this case, and in fact in general about sampling as a whole, is am I really using Bayes networks? Do I really need Bayes networks? Could I just not have looked at the world, look at different days, okay? One day cloudy is true, sprinter is false, rain is true, wet grass is false. I write down a number there. Next day, again, I see what their valuations are. So actually sample the world rather than sample the network. Do you understand what I'm saying? Of course, sampling the world in a day-to-day basis will take as many days as the number of samples, which will take a lot of time. But in some other scenario, sampling the world might take not a whole day. Okay, so one question, if you are actually thinking about it deeply, one question you might be asking yourself is there any difference really between having the Bayes network, which is a model of the world, versus just working on the world directly? Okay, right? Now it turns out, of course, there are all sorts of issues in terms of working in the world. If you actually die in the world, you're dead. Whereas if you die in the model, you're not dead yet, right? So there is that problem. But more importantly, one place here, for example, I was able to give weights to samples because I had CPTs. I couldn't have done this if I was just doing it in the world. Because the world is what the world is. It won't tell you, okay, today I gave you sunny day, but I take $0.7 from you because I gave you sunny day. The world won't tell you that. Do you see what I'm saying? So that's one place where you are in fact using the structure. Okay? Any questions? Yes?
To get these probabilities, actually you have to sample the world, right?
So that is, where did you get these probabilities? Yes. That's pretty much, by the way, the very next topic, which we will start talking next week. Not next week, next class onwards. Okay, how do you get the Bayes network to begin with? We assume that somebody gave us the numbers, that's fine. But if you're learning it from the world, then there's a question as to how to learn it from the number. Okay, and when I start talking about that, and when you understand that, when you come back here, you can easily get confused as to what's the difference between the learning part and the using part. They look very similar, almost. In the learning, the samples are the samples of the world. In using, the samples are the samples of the model. Samples of the model can be generated with as much. If you want 1 billion samples, I'll give you 1 billion samples. Samples of the worlds have a cost. Each sample, you have to go and get it. Okay? And so, again, as you learn that part, you will get more confused about this. So I'm sort of foreshadowing that confusion will occur, but and that you shouldn't be confused. Okay. Any questions? Any further questions? Okay. So the last technique for sampling that I'll talk about today is Markov chain Monte Carlo. In fact, of the 3 techniques we have discussed until now, rejection sampling is very good. Actually, it's a pretty darn good idea. You can easily write it down. But the state of the art in sampling-based methods is not rejection sampling. Is not likelihood weighting. Okay, I'm sorry. What I meant to say is likelihood weighting is a very good idea. Rejection sampling is actually a bad idea. Okay, but in fact, has anybody here heard of the phrase particle filters? If you didn't, that's okay. But if you have heard, particle filters actually do likelihood weighting. And it's like a big idea, that's pretty hot in some areas. And so this idea is actually a pretty nice idea. The last idea I want to talk about for sampling is essentially Markov chain Monte Carlo, which is to essentially realize that Okay, so if sprinkler is true, wet grass is true, then in essence, I have only 4 different states of the network. 4 different states of the network. Okay, and so here's one network state, here's one network state, here's one network state, here's one network state. Okay, and if you sample, basically if I'm here and I resample the rain given its neighbors, that means only rain's value can possibly change. So when you go from one state to other, only one variable's value can possibly change. If no variable's value changes, you did not actually go out of the state at all. So that's why you have self-links. The basic idea of Markov blanket, the Markov chain Monte Carlo, is to realize that essentially these states are connected and there are probabilities of going from one state to another state. And those probabilities depend on the Bayes network probabilities. And that this itself is a big Markov chain. And if you remember anything about Markov chains, and I won't be surprised if you don't at all, Markov chains can have steady state probability distributions, the good ones. The good ones can have steady state probability distributions. And what the MCMC says is if you can simulate this Markov chain and compute its steady state probabilities, those essentially will just give you the joint probability distribution. In this case, conditional joint probability distribution. So what's the probability of cloudy rain given sprinkler true, wet grass true? Okay, so now you can get the joint distribution just essentially by wandering around. Start with a version of a configuration of the state and flip one of the variables. This sort of reminds you of min conflicts algorithm that I mentioned for satisfiability problem. Local search algorithm for satisfiability, where you start with an entire assignment and see if it satisfies all the constraints, and if it doesn't, then pick a variable and flip it and see if you're any better off, and then keep doing it until all the constraints are satisfied. Remember that? It sort of reminds you, what I'm trying to say is it should remind you of that idea. Essentially, I'll start with some configuration of the network. Okay, it doesn't matter which configuration I start from, because if the Markov chain has steady state distribution, the initial state doesn't matter. You'll get to the same, you eventually get the same probabilities. Okay, so now the question of course is, so if I'm here, I'm going to, and I'm about to, so I need to decide, I cannot sample these, right, because these guys are cast in stone. The only things I can sample is either rain or cloudy. What I would like to do is sample them given their Markov blanket. Sample them given the rest of the network. Keep the rest of the network constant. Just try to, if the rest of the network is the way it is, now you can compute what is the probability of cloudy being true, probability of cloudy being false, and then sample. Now if you know that cloudy being true is 0.4, cloudy being false is 0.6, you now actually toss a coin with 0.4 heads, 0.6 tails. And if it still remains cloudy false, you'll stay in this state. If it becomes cloudy true, you get to this state. At this point, you will pick another variable, rain, and then you again sample. Until now, what I said is sample a node given the rest of the network being constant. Now, Markov blanket basically gives you, so the question in this case is, if this network is a huge network, and I'm trying to sample rain, I need to consider the probability of rain given the rest of all the things being evidence, essentially. It's as if everything else is the evidence. These are true evidence and this is the current state. So you have to act as if they are set in stone. That's a huge, P rain given a humongous number of n-1 variables, where n is the total number of variables to begin with. But then we know that really rain is independent of everybody else if given its Markov blanket. So what you really need is not the entire network, but just the Markov blanket. Right? What's the Markov blanket for rain? Okay, what is the Markov blanket for rain? Sprinkler, wet grass, and cloudy. So in this case, it looks as if its Markov blanket is the entire network. But, well, if this network was much bigger, and if sprinkler has many, many children here, and if the cloudy had many, many ancestors, right? And wet grass, then essentially it would still be just this. Markov blanket for rain is cloudy, sprinkler, and wet grass. What about Markov blanket for cloudy? What is the Markov blanket for cloudy? Sprinkler and rain. That's it. So it's smaller. The fact that you're answering this means you now know what is Markov blanket. Okay? And because this is a small network, it looks as if Markov blanket is almost the size of the network. But if it's a large network, Markov blanket will be much smaller than the entire network size. And the last thing I want to do is to show you that if I can always compute the probability distribution of a node given its Markov blanket very easily. Okay? So the way it is if I want to compute the probability of xi dash given the Markov blanket, given its Markov blanket, then I compute the multiply the probability of that variable given its parents times probability of each of its children times the children's parents multiplied. Since that's a dense expression, I'll just show you an example. Probability of rain given cloudy, sprinkler, wet grass is probability of rain given cloudy times probability of wet grass given its parents. Now notice that wet grass is a child of rain, so rain would be one of its parents. The question is there may be other parents. So probability of wet grass given sprinkler and rain. If you do this, you will get the rain's probability given the rest of the network. Even if the rest of the network had many, many more nodes, I will still get the rain's probability just by multiplying these guys. That's the huge advantage for Markov blanket. Once I get this, I now know what kind of a coin I'm about to toss to go from to resample rain. Okay? And all I do is I just keep resampling and see how many times, I'll resample for a while, just keep resampling. And then after about a half an hour or something, now I'll assume I reach steady state. Then I take the next 1,000 samples that I get. And those are steady state samples from which I can get the steady state probabilities. This idea is called Markov chain Monte Carlo. And it works even better in many cases than likelihood weighting. Okay? So I'll stop here. We talked about exact as well as approximate methods for doing inference on Bayes networks. And next class, I will start with one question. You can think about this. You always said probability and statistics, right? What did we do till now? Probability or statistics? And is there a difference? That's going to be the question in next class. Okay?